The semi-major axis of Pluto's orbit varies between 39.3 astronomical units and 39.6 astronomical units. What range of orbital periods does Kepler's third law predict based on this range of values for the semi-major axis? And so this question brings up a bunch of things here. Maybe one of the issues is that if you ask like, well, so is Pluto's orbit exactly an ellipse like Kepler's laws predict? And the answer is, well, not exactly. It varies a little bit. And I think part of the explanation for that is that Pluto's orbit is influenced by the gravity of some of its neighbors, including Neptune, but maybe there's other trans-Neptunian objects that might affect it as well. But in any case, it's, again, not a perfect example. And, maybe that's why it's a dwarf planet, right? Anyways, but what we can do here is recognizing, so let me write down, right? Because we have Kepler's third law. What was that again? It was like r cubed, I think, was proportional to t squared. But it turns out there's another way of writing this that I've seen in astronomy textbooks. Because like the astronomical unit that I've referenced right here, in that unit, the orbital radius of Earth would just be equal to 1, because that's its definition. The astronomical unit is basically the radius of Earth's orbit. And it turns out the semi-major axis is, we're going to treat that basically as if it's an orbital radius, even though it's not exactly, but it turns out it's the appropriate thing to do. For the orbital period, it would be measured in, if it's measured in years, that is, obviously Earth's orbital period is the definition, or originally, I should say it originally was the definition of the year. Nowadays, we have things like leap seconds because the standard for time is based on cesium atoms instead of the orbit of the Earth these days, but that's a whole other story. Anyways, another way that we can write this, though, that I have seen in some astronomy texts is they will say that a cubed is equal, not just proportional to, but exactly equal to y squared. And the idea behind this is that if you have the orbital radius in astronomical units cubed, that will exactly equal the orbital period measured in years squared, because in those units, it's no longer just a proportion, but it's exactly equal. For Earth, it would be 1 astronomical unit. 1 cubed is 1 is equal to 1 year. 1 squared is also 1. So you can kind of see, you can use Earth to demonstrate that this works and why the equality is good there. But in that sense, for these, since we're looking for a range of orbital periods, we can recognize that this thing that I've called y, which is maybe a slightly strange variable to use for a time in a physics class, right? I mean, y is associated with other things, but we're going to think of it in terms of years. But I'm going to solve for y by square rooting kind of both sides and looking at this as the orbital radius, or maybe semi-major axis, raised to the 3/2 power. So hopefully that makes sense what I did there. If you square root both sides, right? Because really, I don't know. Let me look at that for a second there. I'm saying if y squared is equal to a cubed, and I go square root on both sides, that's a really nasty looking square root there. But the thing to recognize is a square root of a cube is a to the 3/2. So in case I did a little bit quick there, I want to make sure everyone's up to speed with where I'm getting this from. And so simply what I'm going to do is I'm going to calculate 39.3 to the 3/2 and use that to calculate sort of the lower end of my range of values for the semi-major axis. Okay, and I'm going to turn to my calculator for that calculation. I'm not sure how to make this notation cleaner. Anyways, I get like 246.37 for that, and maybe I can just round that off to 246 for 3 significant figures, and in turn 39.6 raised to the 3/2 power is equal to 249, 0.1969, etc. But I'm rounding that off again to 249. So that gives me kind of that range of like 246 to 249, and both of those are in, maybe I'll just write it here as in years. Hopefully that's good enough as an answer. Like I said, I'm not quite following some of the usual standards we do for reporting answers in a physics class, I guess. But it looks like it matches. Oh, there's an interesting point here. It says, although Pluto's orbital characteristics are different than the 8 planets, it is interesting that they are not part of the definition of a planet versus a dwarf planet. Oh, I guess I was wrong when I earlier made that sort of like comment that, oh, no wonder Pluto is a dwarf planet. But it turns out it's got nothing to do with what we're talking about here at all. Weird.